It is what I'm going to try right now. Now a player would aim and throw the ball, and yet there is no telling whether it will get through or not. That's what the game is all about, isn't it? Uncertainty. It either happens or it doesn't. In chemistry, dual nature is another game altogether. Keep thinking. Light can illuminate your world at every level. As a matter of fact, it always does. Have you ever paused for a moment to think about it? What happens when we bombard subatomic world with light? Matter, as we all know, is made out of minuscule particles called atoms. It is time that we look into the mysterious properties of light. I'm sure they will amaze you. The dual nature of radiation and matter. De Broglie's relationship. Heisenberg's uncertainty principle, exam decoded. According to Sir Isaac Newton, light was made of tiny particles. But with time, some facts are rewritten, and that's exactly what happened in this case. In 1678, Christian Huygens contradicted this theory. He believed light is made out of waves vibrating up and down. The wave is also perpendicular to the direction of light, thus forming a transverse pattern. This concept of wave propagation came to be known as Huygens' principle. Huygens' theory satisfactorily explained many of the light phenomena. Light wave characteristics are electromagnetic waves, as they are made out of both electric and magnetic fields. And what happens in an electromagnetic wave? Electromagnetic fields oscillate perpendicular to the direction of wave travel and perpendicular to each other. I'm sure you want to know more about light and the wonderful ways in which it behaves. Please do so by visiting our website www.topperlearning.com. Let us now go over an interesting and important observation made by de Broglie. In 1924, de Broglie had stated that the dual nature of light can also be extended to the dual nature of matter. He was of the opinion that if light could be described as a wave, then maybe matter could be conceived as one too. To prove his proposition, he used Einstein's equation. Experiments showed that light exhibited wave-like properties of diffraction and interference. On the other hand, photoelectric effect exhibited that light had aspects of particle nature. The photoelectric effect points to light being made up of photons, thus light exhibits a wave-particle duality. We have already discussed the interesting discovery made by Max Planck. Do you remember that? He had stated that light must be emitted and absorbed in discrete amounts called quanta. So, let us see what Planck's equation tells us. It states that energy is quantized, that is, E is equal to h nu, where h is the Planck's constant, which is 6.626 times 10 to the power minus 34 joules second, and nu is equal to c divided by lambda, where c is the velocity of light. De Broglie's wavelength associated with a mass m moving with velocity c is given by lambda, which is equal to h divided by mc. The momentum p then is equal to mc, so lambda is equal to h divided by p. Lambda is inversely proportional to p, which is the momentum, since h is the Planck's constant. Also note another significant point. The wave character of a particle is only significant if the particle is microscopic and not macroscopic in nature. Similarly, when a baseball with 0.05 kg of mass is thrown with a velocity of 20 meters per second, the momentum is 1 kg meters per second. This situation corresponds to a wavelength of 6.6 times 10 to the power minus 34 meters, which is very negligible. On the other hand, when we have an electron which has a mass of 9.1 times 10 to the power minus 31 kilograms and moves at a speed of 20 meters per second, the wavelength would then be 3.6 times 10 to the power minus 5 meters, which is substantial as compared to its mass. Hence, its wave nature will be observed. Thus, the wave nature of the electron is significant. Now, before we take a short break, I'll leave you with something to ponder on. Can you tell me what de Broglie's opinion on the nature of matter was? While you find the answer, we'll be right back. It's a miracle that curiosity survives formal education, Einstein had said. Am I snatching away your curiosity? I hope not. If you remember, before the break, I had asked you what was de Broglie's opinion about matter. I'm sure some of you can recall this one. He had stated the dual nature of light can also be extended to the dual nature of matter. A big round of applause for those who got it right. Now, moving ahead. Let me have the pleasure of introducing you to a man whose discovery changed the very foundation of physics. I'm talking about Heisenberg and his uncertainty principle. We can only measure any item till the last millimeter, not any further. This uncertainty caused due to the inaccuracy of measurements is further aggravated when it comes to measuring objects that are microscopic in nature. Let's imagine an electron. To measure its location, we have to illuminate it with light. To define the position of the electron, at least one photon has to collide with it, deflect it, and enter the electron microscope. The shorter the wavelength of light that illuminates the electron, the more precise would be its measurement of position. The shorter the wavelength of photon, the greater will be its frequency, and thus the larger will be its energy. If high energy photon collides with an electron, it would transfer some energy to the electron, thus accelerate it more than usual. So, to define the position of an electron more precisely, one should use photons with high energy. With high energy photons, the position of the electron is measured with precision, but its momentum is not certain. However, to reduce the uncertainty in momentum, we use photons of low energy. The momentum of electrons thus measured will be more precise, but its position will be uncertain. So, even though photons having higher energy give precise measurements as they make the electron visible, they end up transferring more momentum to the electron. Therefore, as Werner Heisenberg pointed out, it is impossible to define the momentum and the location of a particle at the same time with equal accuracy. Mathematically, we can say delta x times delta p is greater than or equal to h divided by 4 pi, where delta x is the uncertainty in position and delta p is the uncertainty in momentum. So only one thing can be calculated accurately at a given point of time, either the location of the particle or its original momentum. This concept also holds good for macroscopic particles. However, the energy of the photon is insufficient to change the velocity and position of bigger bodies when it collides with them. Interesting find, isn't it? Thank you, Mr. Heisenberg. Let me just summarize the core concept explained in this episode. Heisenberg stated that it is impossible to precisely define momentum and the location of a particle at the same time. All matter exhibits dual nature. De Broglie and Heisenberg's uncertainty principle holds good for subatomic particles. You should learn for the sheer joy of gaining knowledge. Then, solving problems would seem like child's play. Let us move on to some problem solving. Which of the following has maximum de Broglie's wavelength, provided that they all move with the same velocity? A. Carbon monoxide molecule. B. Electron. C. Proton. And D. Neutron. We asked this question to many students, and this is what they said.
Is it proton?
I'm sure it's carbon monoxide.
Wrong again. Learn with the concepts.
I think it would be electron because the wavelength is inversely proportional to mass as per de Broglie's theory.
That was just what I wanted to hear. Electron is the right answer. Let's move on. Two particles, A and B, are in motion. If the wavelength associated with A is 6 times 10 to the power minus 12 meters, calculate the wavelength of B if its momentum is 1/4 of the momentum of A. We know that the wavelength and momentum are related according to de Broglie's relationship. Therefore, using lambda equal to h divided by p, we get lambda a divided by lambda b is equal to pb divided by pa, or lambda b is equal to 4 into 6 times 10 to the power minus 12 meters, that is 24 times 10 to the power minus 12 meters. Now, moving on to the next question. Calculate the uncertainty in position of a particle with mass 0.5 kilograms if the uncertainty in its velocity is 7.5 times 10 to the power minus 27 meters per second. Now, the uncertainty principle is given by delta x times delta p is equal to h divided by 4 pi, or delta x is equal to h upon 4 pi times m delta v, as p the momentum is equal to mv. So delta x is equal to 6.6 times 10 to the power minus 34 upon 4 into 3.14 times 0.5 into 7.5 into 10 to the power minus 27. Delta x is equal to 1.4 times 10 to the power minus 8 meters. Those many words might have sounded complicated, but you know the math is quite simple. Now, let's try and solve another one. A moving electron has 4.55 times 10 to the power minus 25 joules of kinetic energy. Calculate the wavelength. Mass of an electron is 9.1 times 10 to the power minus 31 kilograms, and h, the Planck's constant, is equal to 6.6 times 10 to the power minus 34 joules second. So, we know that kinetic energy and velocity are related by the formula Ke is equal to half mv squared, and we also know that lambda is equal to h divided by mv. Putting in the values, we get 4.55 times 10 to the power minus 25 is equal to 9.1 times 10 to the power minus 31 times v squared divided by 2. Velocity v squared is equal to 2 times 4.55 times 10 to the power minus 25 divided by 9.1 times 10 to the power minus 31, or v squared is equal to 10 to the power 6, or v is equal to 1000 meters per second. Now using lambda is equal to h divided by mv, we get lambda is equal to 6.6 times 10 to the power minus 34 divided by 9.1 times 10 to the power minus 31 into 1000, which is 7.2 times 10 to the power minus 7 meters. Now for a theoretical one. Explain Heisenberg's uncertainty principle. You should have this on your fingertips by now. I will share with you the answer just after this break. Are you still uncertain about the answer? I am here to tell you. Heisenberg stated that it is impossible to precisely define momentum and the location of a particle at the same time. Mathematically speaking, delta x times delta p is greater than or equal to h divided by 4 pi, where delta x is the uncertainty in position and delta p is the uncertainty in momentum. When we have very precisely defined the location of a particle, we can't say anything about the momentum it had and vice versa. This concept also holds good for macroscopic particles. However, the energy of photon is insufficient in this case to change the velocity and position of bigger bodies when it collides with them. For instance, photons of any frequency cannot change the position or velocity of a cat running into a room. Now that we are confident about this topic, here are a set of important questions that you should be able to answer. Are you ready? What is meant by dual nature of particles? This is a short question for 2 marks. State de Broglie's relationship. How would the wavelength of a moving object vary with mass? This appears for 3 marks. Explain why it is impossible to measure simultaneously the position and velocity of a small moving body like electron. This one comes for 3 marks. There can be times when you don't really understand where you lost marks even after putting in a lot of effort. Well, here are some answers to some very popular questions to help you gain these critical marks. All matter exhibits dual nature. Why is it then a cricket ball when thrown does not exhibit any wave nature? The answer is a cricket ball has substantial mass, and according to de Broglie, lambda is equal to h divided by p, where h is the Planck's constant, which is equal to 6.6 times 10 to the power minus 34 joules second. So, de Broglie's wave is associated with electrons and electron-like particles. Now, let's come back to the question asked. As wavelength is inversely proportional to mass, and as a cricket ball has a substantial mass, its wavelength is very insignificant. Thus, a cricket ball does not exhibit any wave-like character. To round up today's show, here is what our experts recommend for you to remember.
In order to know about the structure of atom, there are 2 important concepts. The first one is the dual nature of the matter, and the second, uncertainty principle. Since it's a numerical related topic, I would like to tell the students to practice the numericals related to the Broglie equation. Sometimes the questions related to the derivation of the de Broglie equation may also be asked. So practice and get a good marks.
It's time for me to sign off. Remember, to learn more, you can always log on to our website www.topperlearning.com. Leave nothing uncertain as you take on those exams. I will see you again with yet another episode. Till then, keep thinking and keep topping.